At the end of the last lecture, we arrived at the separation of variables solution for waves on a string of fixed length L. So it's a sum of products Rn, Qn, where the R function is sine n pi x over L in order to satisfy the boundary conditions that y had to be 0 at x equals 0 and x equals L. And then Qn is a cos omega n t plus b sine omega n t. And the separated equations were d2r by dx squared equals minus kn squared Rn and d2qn by t squared is minus omega n squared qn. And omega and q have the usual relationship to c. So we'd arrived at that separated solution, and I said that any wave on a string could be with two fixed points could be written in that way, and the individual terms were called modes of the string. So it's a modal solution of standing waves. We inserted that solution into the energy density and got a great mass of rather unpleasant looking algebra, and then we integrated that expression from 0 to L to find the total energy, the finite energy on the string E. And at that point, the dawn broke, the sun came up, it all simplified beautifully, and we arrived at the end of the lecture at E equals sigma over n En. In other words, the sum over modal energies, where the modal energy En we found was rho L over 4 multiplied by omega n squared Rn squared plus, Q n squared plus Qn dQn by dt squared. And the final step, which I didn't get around to last time, was to show that En was in fact also constant in time. And in order to do that, I could substitute for the explicit form for Qn up there, which gives us Qn squared is An squared cos squared omega n t plus Bn squared sine squared omega n t plus 2 An Bn sine omega n t cos omega n t, and the Qn by dt is An omega n multiplied by sorry, I can't do that. Is omega n multiplied by minus An cos omega n t. The first term is the sine. Nt plus Bn cos omega nt. And so dQn by dt squared is omega n squared into An squared sine squared omega nt plus Bn squared cos squared omega nt minus 2 An Bn sine omega nt cos omega nt. And so dQn by dt squared plus omega n squared is omega n squared An squared times cos squared plus sine squared plus omega n squared Bn squared times sine squared plus cos squared plus a cross term minus the same cross term and it all boils down beautifully simply to an squared plus bn squared. Now, two very remarkable things have happened in the course of that derivation. What I did was I wrote down a very complicated expression for the total energy, and then two enormous simplifications happened. One was that a whole load of cross terms between different modes turned out to be zero, and here another bunch of cross terms between the cos squared, the cos omega t and the sine omega t also turned out to be zero. And we did all that by putting in explicit solutions. And we could have saved ourselves a great deal of heavy algebra and hard work if we'd been a bit more intelligent. So let me try to explain why those two things happened. And you do that not by looking at the solution, but by looking at the equation. So the equation, let's first of all do the Q simplification. If you go back to the differential equation, we write it as d2qn by dt squared plus omega n squared qn equals naught. And then we multiply that by dqn by dt. The first term is the derivative of d by dt of half dqn by dt squared. The second term is the derivative of half qn squared. So the effect of taking the differential equation, multiplying it by a velocity, is to give us something related to energy. I say related to energy. This equation doesn't have a conserved energy at the moment because there's nothing in there to define energy because there's no mass. But this is a quantity related to the energy. In order to get an energy, you have to multiply by a mass. But what that shows very in one line is that this bracket here is constant. And all you need to do is to work it out somewhere, and that's what the value of the constant is. So so if you do, for example, at time t equals 0, where one of them, where q squared is a squared and q dot squared is b squared, you'll get it in one line. So that's why that happened. The other simplification is much more interesting, and it's to do with, if you remember, when for the first time we arrived at the wave equation, we got there by looking at a normal mode. We looked at a very, very large normal mode, so that the eigenvector of the normal mode traced out a sine wave, and we arrived at the wave equation but by taking a continuum limit of a very large eigenvector. And that suggests that something like this, and of course exactly the same modal decomposition, happened in the energy for the normal mode. So the fact that it's happening here isn't in that sense unsurprising. But the reason that it happened in the normal mode case is because of the normal modes were eigenvectors of a linear operator. So let's go back to the equation satisfied by R, which is d2 Rn by dx squared, and I shall write it in a suggestive form, lambda Rn. And in fact, the eigenvalues are minus n squared, pi squared, over L squared. But this is an eigenvalue equation. This is a linear operator. Is it the right sort of linear operator? Let's do one other very simple thing, which will show that it is the right sort of linear operator. Let's look at one of the terms that arose out of that energy derivation, which was the integral from 0 to L drn by dx drn by dx. And we just plugged in explicitly Rn was sine n pi x over L, and Rn equals sine m pi x over L, and did the integral. But let's do something a bit cleverer. Let's integrate by parts. So we could, there'll be an integrated part. So I'm going to integrate the first term and differentiate the second term. So there's going to be an integrated term, which will be Rn d2 rm by dx squared, evaluated at 0 and L. And then there will be a differentiated term, which is the integral from 0 to L Rn d2 Rm by dx squared x. And this first term is 0 because of the boundary conditions, which are that Rn is 0 at 0 and L. So that term goes away, and we've shown that that integral is equal to that. However, I could have integrated and differentiated the other way around, in which case I would have got, or again we'd have an integrated term that would go to 0, the integral minus the integral from 0 to L d2 Rn by x squared Rm dx. So the two integrals that we had, which were this integral and well no, I'm rushing on ahead too fast. No, I won't. I'll say that in a minute. So what I've just shown is that this integral equals this integral. And look, what's happened is here the operator that occurs in my differential equation is acting on the second term. Here it's acting on the first term. That little bit of algebra, that little bit of calculation that shows that integral equals that integral is precisely what you need to show that this operator is self-adjoint. I haven't used any properties of the R functions except that they satisfy the boundary conditions. So for any two functions that satisfy the boundary conditions, I've shown that this equals that. And that tells us that the operator is self-adjoint, and it's linear, and therefore we have eigenvalues and eigenvectors with all the usual properties. And the inner product will be, so if I call the vector n, I define that to be sine n pi x over L, then the inner product, mn, I will define to be the integral from 0 to L Rn Rm x, and I immediately know that that is 0 if n is not equal to m. And we can do it in exactly the same way. We replace this by the eigenvalue times Rm. We replace this by the eigenvalue times Rn, and we subtract them. It's exactly the same proof as in linear algebra, and we get an integral multiplied by a difference of eigenvalues equals 0. So either the eigenvalues are the same or the integral is 0. All of these integrals are 0 if the eigenvalues differ. So all we have to do is work out what's the value of that when Rn equals Rm, in which case it's L over 2. And so these vectors are not normalised to 1, they're normalised to L over 2. So the whole business that we did in the end of the last lecture boils down to a little bit of linear algebra, which forces all these integrals to be 0 and to be related to each other. And that's why the energy splits up into modal energies. And the modal energy, just to repeat it, is En is rho L over 4 omega n squared An squared plus Bn squared, where that bracket is just the amplitude of the mode at its antinodes. So I'm going to leave waves on finite length strings for the moment and go to what happens at boundaries between strings of different kinds. Let me return to the background state. The background state is a tension string carrying a tension T. And what I'm going to do is create a boundary so that the string here is not the same as the string here. So here it has density rho 1, and here it has density rho 2. And that sounded very easy. The question is, how do you actually join two strings together? And you'd actually, there are quite a lot of ways of doing that, but simply having two lengths of string and buttoning them together is clearly not it, especially if you're going to pull with a substantial tension. So we need some contrivance on the boundary to do that, which might be some kind of interlocking hook or something that joins them together, or you might knot them together, or you might splay the ends out and splice them together. And all of those have the effect of a splice will introduce a short section where the mass per unit length is row 1 plus row 2, because you've got all the twines from both strings twined together, or else you've got some extra mass on the boundary given by this piece of apparatus that's joining them together. So a realistic boundary will, in addition to that, have some mass on the boundary as well. Now I'm going to treat that case second. Okay. So at the moment I'm going to do a mathematical boundary where there's just an abrupt boundary from one density to the string density to the other with no extra mass. And that gives a very simple and soluble problem. So what I'm going to do with this boundary is send in waves from one side. So if x is that and the boundary is at x equals 0, I'm going to send in waves from the negative x side. And what will happen at the boundary is that some of the waves will be reflected and some of the waves will be transmitted. Now it's best to solve boundary value problems with complex variable waves. So I'm going to write the input wave as e to the I omega t minus kx. So that's the input wave. The reason for doing that is I can then write the reflected wave as r e to the I omega t plus kx. And I haven't made any assumption about the phase of this wave relative to this wave, because if it's not simple, then r will just turn out to be complex. So r is able to handle both the amplitude and the phase of the reflected wave. If you did this with sines and cosines, you'd have to have, if you put in a cosine wave, you'd have to consider the possibility of both a sine and a cosine reflected wave. So it just simplifies the number of things you have to write down if you do it this way. It's not the only way of doing it. Now there'll be a transmitted wave, e to the I. And what should I put in there? Well, what's happening on the boundary is the string is going up and down. And the up and down that the string is doing on the boundary is the same on both sides. And therefore, the frequency of this has to be the same. The frequency has to be the same throughout. So I can put in omega t. But I do know that the k's must now be different, because on this side of the boundary we have omega over k equals C1, and on this side of the boundary I have omega over, so I'll call this K1, K2 equals C2, and this is equal to the square root of the tension divided by rho 1, and that is the square root of the tension divided by rho 2. So this K here is K1, and this is a forwards going wave minus K2x. So let's discuss the boundary conditions that apply at this boundary. At the boundary, we clearly have y1 equals y2. The displacement of the string on the two sides of the boundary is the same. But we also have dy1 by dx equals dy2 by dx. Why is that? If we remember that there is tension running in the string, where the string is being pulled to a tension in both directions, and that will, if you don't put a wave on that, that makes it straight. If you put a wave on it, there will be curvature which will satisfy the wave equation. The wave equation contains a second derivative, which means that the first derivative, and there is a discontinuity in the second derivative because if we write the wave equation as d2y by dx squared is 1 upon c squared d2y by t squared, or I could write it as rho over t d2y by t squared. What happens on the boundary is that there is a discontinuity in c, or equivalently a discontinuity in t, which means there is a discontinuity in the second derivative, which means that the first derivative must exist on the boundary. Okay? So there's a difference in the curvature across the boundary, but the slope has to be continuous. So if I put all of that into my equation, I could in principle consider an incoming wave from this side, but if the situation is as I've described it, with the waves coming in from the left and no waves coming in from the right, then there's nothing over there to produce waves that's coming in this way. So that ought to be a sufficient set of solutions to do the job. So I put in all the terms on the left and evaluate them at x equals 0, and which is where the boundary is, and I get e to the I omega t plus r e to the I omega t. And on the other side, I needed an amplitude here, which I'm going to call t for transmitted. And that's equal to t e to the I omega t. And very conveniently, the time cancels throughout to give us 1 plus r equals t. And then if we differentiate on the left, we will get minus I k1 e to the I omega t plus I k1 r e to the I omega t equals minus k2 t e to the I omega t. And again, the times cancel throughout to give us, and I'll cancel a minus I throughout to enable me to write that as 1 minus r equals multiplied by k1 equals k2 t. So these two equations determine the two coefficients r and t. Of course, the assumption of an input wave with unit amplitude is not a restrictive one, because I can multiply the whole solution by any constant I like at the end. It's just that, fundamentally there are only two undetermined constants in this, apart from the overall amplitude, which are the relative size of the reflected wave and the relative size of the transmitted wave, and they're governed by r and t. So this is the most economical way of writing down a general solution. So if I multiply the top equation by k1 and add them, I will get, well, let's go on to a new board to do that. So I'm going to multiply the top equation by k1 and add them, and I shall get 2k1 equals k1t plus k2t, giving me t is 2k1 over k1 plus k2. And if I substitute that back into the first equation, r is t minus 1, which is 2k1 K1 minus K1 minus K2 over K1 plus K2 is K1 minus K2 plus 2. So those are the expressions for the reflected and the transmitted coefficients in terms of K. I very strongly recommend that you don't try to remember those, and I'll now tell you why. Because if I gave various different relations back here, or different ways we could characterise. I could characterise the two sides of the boundary by K, the different values of K, the different values of C, or the different values of rho. So if I substitute K is omega over C into that equation, I get T. So I'm going to put K I is omega over Ci, and so I'll get T is 2 omega over C1 over omega over C1 plus omega over C2. If I divide top and bottom by omega and multiply top and bottom by C1, C2, I'll get C2 over C2 plus C1. And similarly, R will get me omega over C1 plus omega minus omega over C2 over omega over C1 plus omega over C2, which is C2 minus C1 over C2 plus C1. So we get an expression in exactly the same form as for R and T, but the 1's and 2's are all the other way around. So here in the denominator we get K1 plus K2, and here we get C1 plus C2, so that's the same. Here in the numerator we get K1, here in the numerator we get C2. Here in the numerator we get K1 minus K2, here we've got C2 minus C1. All the 1's and 2's are the other way around. And the other way of doing it is in terms of densities. So if I now put C is the square root of T over rho, I, rho I. Again, we're substituting something. We've got something in the numerator, root T, which is constant and will cancel throughout. And we've got something in the denominator, the square root of rho. And because it's in the denominator, the same transformation will happen and will boil down to root rho 1 over root rho 1 plus root rho 2, and root rho 1 minus root rho 2. So in other words, all the 1's and 2's change place again. Now, it's clearly not going to be sensible to try and get those the right way around. The only sensible thing to do is to remember how to work them out. So that's what you've got to do. So that's the structure of the thing. So let's just take a particular example. Let's take rho 2 is 4 rho 1, and that has the consequence that C2 is root T over 4 rho 1 is 1/2 C1. So if we go into this second version that I just wrote down, we will get that the transmitted wave is and I'm certainly not going to try to remember what I just wrote down. C2 over C1 plus C2, and R is C2 minus C1 over C2 plus C1. And if we just put in the half, here we will get 1 over 3/2 is 2/3. And so that's minus a third. So I was just mentally checking that the original equation was 1 plus r equals t. That's 1 minus a third is 2/3, which is correct. What will happen if we send in the waves from the other side? So waves well, obviously, what will happen is that we'll interchange 1 and 2 everywhere. And so I'll call these with primes. T primed will be 2c1 over c1 plus c2, and r will be c1 minus c2 over c1 plus c2. And this will be 2 over 3 halves is 4/3. This will be 1 minus a half is a half over 3 halves, which is plus 1/3. So again, we get 1 plus r equals t, but r is positive, so t is greater than 1. And so that is t prime, and that is r primed. And numerically, that's showing something quite interesting, which is this is equal to the negative of that, and this is bigger than 1. Is there a problem with the transmitted wave having a bigger amplitude than the wave we put in? Well, no, actually, as long as the energy is conserved. So let's now have a look at the conservation of energy on boundaries. So what does it mean to say that energy is conserved on the boundary? What it means is that the energy that's flowing in to the boundary in the input wave must flow away from the boundary either on one side or the other, and not pile up on the boundary, because we know that's not what's going to happen. So the energy that arrives must leave again. So that means the incident flux, which is the flux in the incoming wave minus the flux in the reflected wave, ought to equal the transmitted flux. So the formula for the flux is minus t dy dx dy dt. We just step back at our boundary conditions. Oh, here they are. We add dy1 dx is dy2 dx. So this term here, the dy dx term, is continuous across boundary. The tension is also continuous across the boundary. Dy by dt, well, if y1 equals y2 on the boundary, just differentiate, the rate of change of this has to equal the rate of change of that. So this is also continuous across the boundary. So the flux is continuous across the boundary, and therefore energy will be conserved. So actually, calculations of conservation of energy at boundaries are really, I mean, they must come out right. They can't fail to, because the flux is conserved. So it's just a question of whether we can do it another way, essentially. We've already proved it in complete generality. So let's do it for a particular input wave. So because the particular coefficients that I've come up with, the c's and t's, are all real, let's actually specialise now to a real wave. So let's take the real part of this solution and write them all as cosines. So what we have, so on the input side we have cos omega t minus k1x plus r cos omega t plus k1x. And on the output side going to do a flux calculation on the left, on the one side, which will give me a flux. And actually, I think I'll put in an overall amplitude here as well, A. So just so that we've got something with dimensions of length, so that all the R's you'll observe are just numbers. So by putting in an A, I've given everything the dimensions of length, which it ought to have. So that's my physical Y. So I need minus T, I need dy by dx, which is a minus from differentiating the cosine, and a minus from differentiating x is a plus a k1 sine omega t minus k1 x. I'm going to evaluate it at the boundary, so that's just going to be sine omega t. And then I'm going to have the spatial derivative of this, which will have a minus from differentiating the cosine and a plus from differentiating with respect to x, which will be minus AR K1 sine omega t. And then the time derivative will be there'll be an overall minus from differentiating the cosine. Will be minus a sine omega t, and then we'll have plus this will be minus a r sine omega t. So we take out a minus sign from there with here, giving us t. We go to take out a k1 from there, and an omega. Oh, there should have been an omega in here, shouldn't there? Omega from differentiating with respect to time. A squared, and we'll then have that times, we'll get a squared sine squared, we'll get minus a squared r squared sine squared, and we'll get a cross term that cancels. You ought to be getting used to cross terms that cancel now. It's never an accident, remember. We've already shown why that works. So we get a squared 1 minus r squared sine squared omega t. So that's the flux on the left, and it involves 1 minus r squared. But it involves tk1. So the flux on, so that's f1. Now the flux on the other side, f2, will be tk2 omega a squared t squared sine squared omega t. Be a much simpler calculation. So our requirement is that f1 equals f2. And so it doesn't matter if t is bigger than 1, provided the k is sufficiently, this k is sufficiently small compared with this k. So let's actually write both of those in terms, let's eliminate the k in favour of an omega. So f1 will be t omega squared a squared. So k is omega over c, c1. 2 is t omega squared over c2 a squared t squared. So energy conservation requires this to equal that, which is 1 minus r squared over c1 equals t squared over c2. So that's energy conservation. back to our numerical example, we had R prime for the second case was 1/3, T prime was 4/3, and no, I'm getting ones and twos back to front if I'm not careful. I actually wanted to look at that second case, but let's look at the first case first. So on the first case we had R is minus 1/3, T is 2/3. We had 1 minus 1/9, and we had over C1 was T squared is 4/9 over, and the question is what's C2? This was the case where we were going from a lightweight string to a heavyweight string. This C was slower, so this was a half C1, and so we get 8/9 equals 8/9. However, if we interchange the ones and twos judiciously, we get the second case, which was R prime is plus 1/3, T prime equals 4/3. But this time we're coming in, we're going out on the faster string and coming in on the slower string, and so I get 1 minus 1/9 over C1 equals 16 over 9 divided by 2C1, which is again 8/9 equals 8/9. So there's nothing wrong with amplitudes bigger than 1, output amplitudes bigger than input amplitudes, as long as the other coefficients conspire to make the energy conserved, which of course they always will. So that's how to do waves on a boundary with input cosine waves. However, the fact that the reflection and transmission coefficients can be written in terms of constants like C and or rho, and not in terms of the parameters of the wave, K, suggests that the actual wavelength of the wave played no role in that proof. Or in fact, the fact that it was a cosine at all played no role in that proof. And that's true, it doesn't. So let's do it a different way. So we have the same boundary, x equals 0, rho 1, rho 2, C1, C2. We have a general input wave, f of, but now at this point, because what's going to happen on the boundary is really a function of time but not x, we want to prioritise the time. So although I've been writing my forwards-going wave as x minus ct, I'm now going to change tack. I'm going to write it as t minus x over c1. Okay? And then there will be a reflected wave, g of t plus x over c1. And over here there will be a transmitted wave, h of t minus x over c2. And then on the boundary, we will have, we evaluate this at x equals 0, we evaluate that at x equals 0, and similarly that. And we require that the y is continuous, which gives us f of t plus g of t equals h of t. And then we require that the spatial derivative be continuous on the boundary also, which is 1 over c1 f prime of t minus f prime of t plus g prime of t equals minus 1 over c2 h prime t. Now, let's just look back at what we did a little before. We multiplied the first equation by k, which is the equivalent to differentiation. So I'm going to differentiate this with respect to time. I know that k is a spatial derivative, but what I need here is temporal derivatives to get rid of the temporal derivatives down there. So that was just a look back for a suggestion. And the suggestion is differentiate with respect to time. So if I differentiate that with respect to time, I get f prime of t plus g prime of t equals h prime of t. And if I multiply this equation by C1, well, no, let's multiply that one by C1 and add, and that will give me the G's will. Sorry, it's this one. No, right. So sorry, I mean subtract. I want to get rid of the G's. Don't I want to get everything in terms of F. So I'm going to subtract this from this, which will get me 2 f of t. I'm subtracting that from that. Will be f prime of t. Sorry, h prime of t. 1 minus c over c2. And so h prime of t is 2c2 over I subtracted that, so that should be a minus 1, shouldn't it? Let's do that again. It's important to get the signs right. It took a while. So here we had f plus g equals h, which is correct. Here we have minus f plus g is minus h, and I've multiplied through by c1. That's correct. F prime plus g prime is h prime. So now I'm subtracting that from that to give me 2f. I'm subtracting that, so that comes in with a plus, and that. So yeah, these are both. So they're both pluses. Right. So 2c2 over c1 plus c2 f prime of t. And obviously I can integrate that to give h of t is 2c2 over c1 plus c2 f of t, potentially plus a constant. That constant is nothing to do with the input wave because it doesn't depend on f, so it's not really part of the solution. And similarly, if I did the other thing, I'd get g of t is c2 minus c1 over c2 plus c1 t. So I mean, if I now substitute h of t into that equation up there, I get g of t is h of t minus f of t, which is that minus 1 times f, which is that. Now, if my luck's held, and last year it didn't, so let's have a look. If I now look at those reflection coefficients, we've seen them before. Side. Here we go. Whoa! 2, obviously, no. Right. 2c2 over c2 plus c1, that's the same. c2 minus c1. This is the one I got wrong last year. c2 minus c1. c2 minus c1. Yes, right. Okay. So, whatever wave you put in, you get a certain fraction of that wave coming back, a certain fraction of that wave going forwards, and it doesn't matter what shape the wave is. It's just a bit easier to calculate with sines than with all these arbitrary functions, but it'll work for any old wave. So, and you can, obviously the energy will work with that format as well. So all of that was with my idealised mathematical boundary where the density change is abrupt from one density to the other. Tomorrow I'll put in a mass on a boundary, and then I'll show that we do get something that depends in a much more interesting way on the structure of the wave, and the fact that it's a sine wave then does matter. And then if there's any tidying up to do, I will talk about one or two other things tomorrow, which will be either impedances or Stokes coefficients. And if anybody has any questions, I'll try to keep 10 minutes at the end for stuff that people want to ask. Okay, that's where I'll stop for now.